Hi, my name is Henrique and I'm a test automation engineer at Typhoon HIL. Today I will show you how to automate your motor drives controller protection tests using Typhoon HIL's ultra high fidelity models with third-party ASAM XIL compatible solutions, like tracetronic ecu.test. With ecu.test, users can intuitively create test cases in every development phase and run them automatically. One example of a test case that is very time-demanding, highly risk regarding safety issues, and hard to replicate in the lab or field is a motor drive's fault response. Recreating this test scenario with real equipment and power hardware can potentially have destructive effect to the equipment. However, this can be easily overcome by using Typhoon HIL's ultra high fidelity real-time models, like the one I will show you in this demonstration. Let's take a look first at the setup we'll be using and then at the motor drive model that we'll be simulating. Our test bench will use our 200 nanoseconds time-step Typhoon HIL404 real-time simulator, ABB ACS880 industrial motor drive ECU, and an interface board specially designed to scale the required analog and digital interface between the HIL device and the motor drive controller. The ECU is configured for external control with factory macro enabled. Start-stop, direction, and reset commands are accessed through the controller's standard I/O interface directly connected to the HIL outputs. The model comprehends all common motor drive power circuits, including the three-phase voltage source, the three-phase rectifier, the DC link with ingress circuit and braking resistor, the three-phase inverter, and the squirrel cage induction motor. All necessary analog and digital signals are mapped in the interface board and connected to specific HIL analog and digital interfaces to make the controller feel like it's operating with its real hardware, turning the simulation environment transparent to the controller. In order to test the motor drive ECU fault response, we need to emulate a fault in the circuit. We can test, for instance, short circuit protection, and check with ecu.test if the controller detects the fault and sends a command to the drive to stop the machine. The inverter IGBTs in this simulation are controlled by the PWMs generated by the ECU. We can simulate a short circuit in any of the inverter switches by bypassing the ECU PWM command. Let's take a look at ecu.test on how to implement a test case for this. We will build this test case with three packages inside the project. The first package will be a setup function. This function will configure all simulation parameters, start simulation, put the drive in steady state condition with nominal speed and torque, and turn on the drive's power supply. We will send a command through the I/O interface to start the drive, set the direction to forward, and wait some seconds until the drive reaches a steady state condition. We can verify this condition by asserting torque and speed at nominal set point. Then, we will have the test case package. In this test, we place the motor speed and torque to full load. Then, we pass control of the IGBT switch S8 top to the software. By doing this, we can force an IGBT short circuit and bypass the PWM signal from the controller for this specific switch. When we force the switch to short circuit, we can read the torque and assert that the torque is cut off in the simulation within 100 milliseconds timeout. We then send a stop command to the controller to stop the drive. We use the post-action block to reset faults and re-establish steady-state condition in the simulation to make sure the drive recovers from the fault. Finally, we have a TearDown package that in this case is only used to perform the stop simulation job. We can press play to execute the test and follow the test steps in real time. After test execution, we can analyze the test report in details. In this general overview, we can see the test results and test cases summary. We can also check the execution time for the tests. In this left drop-down menu, we can navigate through specific test case results, check each test step, and plot signals that we recorded during the test, in this case motor speed and torque. Other protection functions like overload, overvoltage, overtemperature, and power loss write-through can also be easily fully automated in a consistent and repeatable process by rearranging similar test steps and configurations. If you have any additional questions or topics that you'd like us to cover, let us know in the comments. Thank you for watching.